So we've been talking about potential energy, and potential energy is energy that gets due to the interaction between pairs of things within a system. And we have several equations for different kinds of potential energy associated with different interactions, right? So if we have two objects that are interacting gravitationally in our system, then the potential energy associated with that interaction is minus g times the mass of one times the mass of the other, divided by the r, where that's the magnitude of the relative position vector. So that's the separation of these two objects. We have electric potential energy, which has a very similar form. There's a constant. This one is 1 over 4 pi epsilon 0. And then we have the charge of one object and the charge of another object over the separation between them. That's a magnitude of a vector. And we also have an easier way of calculating gravitational potential energy near the Earth's surface, because it's the distance to the center of the Earth is such a big number compared to these small displacements. The change of gravitational potential energy near the Earth surface is the change in this quantity mgy, where y is the height above the Earth's surface. And sometimes we write even the gravitational potential energy near the Earth's surface is just mgy. We know that there's a big constant term where it's this with the radius of the Earth in there, but that's not changing, so we often just leave it out. And we've looked at different processes where potential energy where energy in a system of interacting particles flows between kinetic energy to potential energy back again. We looked at a comet orbiting a star, and we saw that gravitational potential energy decreased and kinetic energy increased as the comet got close to the star, and then when it got farther away, the opposite happened. And we've also looked at it in situations involving charged particles. So we've thought about what would happen, for example, if two electrons started far apart and came towards each other, and we chose the two electrons as the system so that there would be a electric interaction. We thought about how kinetic energy and potential energy would flow. And let's just think about that again for a minute. If we have this system of the two electrons that are approaching each other, let's remind ourselves we have an equation for electric potential energy here. Which of these graphs correctly shows the kinetic energy of the two electrons, the electric potential energy of the two electrons, and the sum of the two in this situation where we choose both the electrons as the system? So if you're not sure, think about something that you really can think about. What's happening to the kinetic energy, for example? Okay, so that's not very good. So let's try to remember what we're doing here. Okay, so there are a number of ways to look at this graph. So let's think about it. So one thing we can do is actually just look at this equation for electric potential energy and see what that's going to look like. We've got this 1 over distance thing, right? So when R is large, potential energy gets very small. When R is big, when R is small, it should be big. When R is large, it should be small. And now we have a sign issue, right? This positive constant. So the question is, these two things can be positive or negative. What are they in this case? They're both negative, so the product should be positive, right? So what we have here is a constant times 1 over R. We know it gets small out here. It's positive, so it approaches infinity as they get extremely close together. So in this particular case, for these two electrons, looks like the potential energy's positive. Now, what's happened? Just think, never mind the potential energy. What happens to these two electrons? They're coming together, and how are they interacting? They don't like each other, right? They're repelling it. They're exerting forces, repulsive forces on each other. So there's a force. So if they're repelling each other, what's happening to their speeds as they come? Yeah, the speeds are decreasing, aren't they? If the speed is decreasing, what's happening to kinetic energy? Decreasing. Okay, so kinetic energy is getting smaller as they get close together. It means it's bigger if they're farther apart. And can kinetic energy ever be negative? No, it can't, right. So presumably we have kinetic energy doing something like this, where it's, and there probably is a limit, because if they got to the point where they touched, which is hard. Now we're not really quite sure what the radius of an electron is, so maybe we'll hedge and not draw that there. But so the kinetic energy would do something like this in this case. Now, we had a conversation last time about how we add curves. You find an easy place, right? And a really easy place is when one thing's 0 and something else isn't, right? Because 0 plus something is something. So what's a place where one thing's 0 and... Yeah, so how about here? So here's U, that's 0. Here's K, that's that. So what's K plus U? It's equal to K, isn't it? Yeah. And now, is anything doing work on this system? No, we didn't mention anything else. So what should be true of this? The total energy should be constant. So we expect a straight line, right? So this is drawing this line here, that seems to be a very attractive distractor, but doesn't have any mathematical significance. It's just some sort of, I don't know, gestalt thing. It looks like there should be a line there or something. That's not the sum of those two curves, is it? So you need to actually check. It's okay to guess, but then you got to check it. All right? Now, what would happen if this was, what if there were a proton and an electron? Yeah, so let's think about proton plus electron. We'll draw it over here. So this would be positive. That would be negative. So now, what does the potential energy curve look like? So it's negative because one of these is positive and the other is negative, so it's going to be negative. So we have a curve that looks exactly like the gravitational potential. So this is U electric for proton and electron. This is electron and electron. And what happens to the kinetic energy? Well, as they get closer together, what happens? They're going to go faster. So it's helpful to draw the forces, isn't it? Here we've got, so they're speeding up, so what's happening to kinetic energy? Getting bigger. Okay. So we have kinetic energy getting bigger. And now the sum of k plus u depends on what we started with out here. If we start with them at rest, so that they have 0 kinetic energy, then we'd have that for k and that for k plus u. If we start with them moving toward each other, they'd have a little more. So it depends on the initial. Okay, questions about this? We're going to keep drawing potential energy curves. Kinetic energy decreases as they get close together, because remember, I'm not being very careful about. So this is the distance between the particles, and this is energy. So we're talking about the 2 electrons, right? So they start with some kinetic energy. So we'll think about the momentum principle here. The momentum of this one, it has some momentum, moves this way, but there's a force acting on it that way. So that's an F parallel, right? So it's going to change the magnitude, slow it down, slow it down, slow it down. So let's look at kinetic energy here. It starts out with some large positive value, and it gets lower and lower and lower until it goes to 0. So does that capture what we're talking about here? Yeah. So we have to think about the particular system. Gravitational energy is easier because it's always attractive each other. They're always an attractive force. So. Okay. So I want to talk for a minute about, we're going to start talking today about systems of more than one particle. And so I want to talk for a minute about some things about multi-particle systems. We're going to talk about some reactions, things reacting to make a more complicated particle.